Okay, so good morning, everyone. So remember that before we was talking about LU factorization, I mentioned there's an example, right? Suppose you have a given matrix, and then you have a lot of input vectors, okay? And then you have to solve the linear system AXK equal BK again and again, okay? So you see, we see that, so if I share with you my MATLAB program, so suppose I share my MATLAB here. Okay, so solver. So what is solver? So solver is essentially, let me share the solver. So the solver is a simple MATLAB program. So very similar to the spirit of the lab question. So suppose you have a matrix, say 50 by 50, right? So it's a matrix A. And then you have like 100,000 input vectors, okay? And then you solve it by two methods. So the first method is you solve by backslash command. So this one is, just Gaussian elimination. And the second elimination, yeah. And the second method is you compute the LU factorization, and then you solve by LU factorization. You see that if I run it, okay, so now if I run it, so I save, and then, so what is the question? Sorry, tick and tock. So tick and tock is similar to CPU time. Okay, so remember in the lab we use CPU time, but tick and tock is just another commands to start the clock. Tick, start the clock, and tock, end the clock, and it gives you the elapsed time, how many seconds. Okay, so just help tick and tock, and you will see it. So it's just the same. In the lab we use CPU time, remember? Okay, so now if I run it, yeah, so now if I run it, oh, maybe I share the command windows, yeah. So if I run it, you see that tick and tock give you the elapsed time. The first line is the elapsed time of the LU factorization, and the second time is the LU the first is the Gaussian elimination, yeah, and the second number is the LU factorization. And you see that LU factorization is always faster. Okay, and that is the reason we study LU factorization. So now we will discuss why is that the case, at least in these lectures. So we have to look at the theory, okay? So now, so we go back to the slide. So this one is just the definition of the upper triangular matrix and the definition of the LU factorization. And then, you solve AX equal B by two steps, Ly equal B, and then UX equal Y, okay? But then we discuss, how we computed the matrix U and the matrix L. So essentially just a product of Gaussian elimination, yeah? But, sometimes you have to swap the rows, yeah? So that's called pivoting, yeah? So pivoting, then when you interchange the rows, what it does inside MATLAB is just multiply by a permutation matrix, yeah, the permutation matrix P. So you don't have the original A equal LU, but you have PA. You swap the rows of A and you got equality equal LU. And then we solve, like we solve Ly equal PB first, and then solve Ux equal Y. And then we discuss that, well, so this one you can read the lecture notes. This one is just another reason why you need to swap the rows, you know. So we skip this, but you can see the exact, you can read about this example in the lecture notes, yeah. So essentially what it say is you have a matrix, just a simple 2 by 2 matrix, very well conditioned, okay. So condition just equal 4, yeah. And then you can give the exact solution, okay. So this one just 2 by 2 linear system, you can solve it to get exact solution. But when you run the LU factorization, okay, then so let me let me try to run this one for you. So suppose I have a look at math pivot. So what is, so I should have this in my directory. So you see, if you see the editors, yeah. So essentially you have the matrix A, okay, and A is just mu1 1 1, yeah. And then in this case we can compute the L matrix L and the matrix U exactly, okay. And when you run it, so now when you run it, so now you see that the well, there's two cases, yeah. So this one is when we swap the two rows. So this one is after we swap two rows, and this one is before we swap. Okay, so two cases. Now, so as you see, mu1 is on the top and 1 1 is bottom, right? And this one is the second case when we swap it. And so now let me run it, yeah? So you see that now if I run the first case, okay, so if I run the first case, you can see the relative errors is big, you know, like 7%, you know, for a small, for a very small size of the matrix, and the matrix is very ill conditioned, okay. But now if you swap the rows, okay, so now if you swap the two rows of the matrix A, so now if I swap, so again this one is in the folders of the chapter 3 in Moodle, yeah. So you can have a look in that folder. So now suppose I swap the rows. So now I swap the rows, yeah. Then I got a different LU factorization and I run it again. So whenever I run it again, then you can see that now the relative errors is 0 and X star is now exactly equal X. So remember, X star is just approximation and X is the exact solution by the formula. You see, so the difference, you see the difference here, so the approximation is off by 0.1, right? I mean, here is exactly correct. So that is another reason why you need to swap the rows, yeah? So at least in this example, show you another reason to swap the rows of the matrix. And this one, you know, can be explained, okay, by the following theorem. So So the theorem say that, okay, this theorem was proved by Wilkinson in 1961. So essentially it say that if you have the LU factorization of a matrix, yeah, then essentially inside the machine, what you have is just L star. So L star is some approximate of the L. Remember the floating point representation, it always introduce some errors. The question, put my RAM memory desktop run 11 gigabyte MATLAB. What do you mean 11 gigabyte MATLAB?
Yeah, because the MATLAB, I looked at the size is 11 GB. So that's why I use the online one. I'm not sure if my
You mean 11 gigabyte is the full MATLAB?
yeah, full MATLAB, yeah.
Yeah, you can download it and install it, but it will not use up to 8 giga RAM when it run it.
Okay, so still can run. Thank you.
Yeah, you can do it. No worries. You just run it. Okay.
Yeah.
Okay. So back to the theorem. Yeah. So the theorem just say that. Okay. So now, what happened is, A is the original matrix, and you introduce some errors here. You know, when you have the LU factorization inside the floating point system, and that errors can be bounded by this inequality. And you can see that if this constant is big, then the upper bound can be big, right? And that is exactly what happened here in our case. Okay, so here before, this one is the change in the matrix A, and this one is the change in the solution of the linear system. Okay, so again, the upper bound can be big if the norm of the matrix L star or U star is big. Yeah, and that is what happened in our case. Yeah, in our case, you see, when you take the condition number of the matrix L, it will be of this form, 1 plus 1 over mu. And remember, mu can be very small, you know, mu can go to 10 to the minus, say 10, and 1 over mu can close up, okay? And that's why people introduce pivoting, so swapping the rows, yeah? So partial pivoting is just a special way to perform the row swap so that the pivot element has a larger magnitude than other entries below it, okay? And MATLAB use it, so MATLAB use it. And so this one is an example, show you how MATLAB perform the LU factorization of this matrix, okay? So you can trace through it. And you see on the right is the index of the rows. And you can see that when you swap the rows, then these numbers are changing. See, this one is mean like you swap row 1 and row 2, right? So this one record the row swapping. And you see number 5 goes up here because it's the largest in magnitude. And then you perform the Gaussian elimination. And then you store the multiplier here. You see, because this one is just a way to somehow to save the memory. Okay, so they reuse the lower part of the matrix to store the coefficient. Okay, and the coefficient will be the matrix U. Okay, so that is how MATLAB is doing it. So they compute. So remember, the green one is just the factors, the factors of the matrix U. And if you trace through the process, eventually, you will see that the upper part will be the matrix U. And the lower part is the matrix L. Yeah, so when you trace through the coefficient, you see, so the matrix U is here, the upper part, and the matrix L is the lower part, okay? And you can see that because you trace through the, like the interchanging of the rows, then you get the permutation matrix something like this. And PA will go LU. Okay, so you can check. So, okay, so we talked about this already, yeah. And so now we need to explain, okay? We need to explain why LU factorization, is faster than backslash command. So this is the theory. So the theory is based on counting the number of operation. Okay, so what is floating operation? So either you add two numbers while subtract is add in a negative number, or you multiply while multiply by the inverse is the dividend, right? So in the sense that any operation plus, minus, multiply, or divide is called one floating operations, okay? Where A and B are floating point numbers. So you see, we counting how many floating operation for each algorithm. So now suppose I want to compute the inner product x dot y, okay? Then I need to use only 2n flops. So flops is the shorthand of floating point operation. Yeah, FL called from floating off from operations. Yeah. So why is 2n? Well, because you take x1, you multiply by y1, so one multiplication, right? And then x2 multiplied by y2, so two multiplication, right? So eventually you need n multiplication, yeah? Then how many addition? Well, actually you need only n minus 1 addition. So totally is 2n minus 1. Yeah, but for n is very big, like n is a million. Then 2n minus 1, is very close to 2n. So we just ignore the minus 1. Yeah. So we say that is about 2n flops. And so now computing the LU factorization will be around 2n cubed over 3 flops. So why is that? Well, so this one I have to explain on a piece of paper, yeah? So why we need only 2n cubed flops? So remember, you compute the LU factorization by Gaussian elimination, right? So you have a matrix like this. So this one is your matrix A11, A12 up to A1n, right? Yeah. So A21, A22 up to A2n, and so on. So the last one is AN1, AN2 to ANN, right? So how do you do the row operation? Well, first you have to compute some factor, right? So that you make this equal 0, right? Yeah. So the first row is still the same, right? Yeah. And then you compute some operation, then you know that this one will equal 0 on the way, yeah? Yeah. And now, so how many points, how many entries do you need to modify? How many entries you need to modify? So how many entries? So those entries, that has to be equal 0, right? By the algorithm of Gaussian elimination, yeah? So then those entries you have to modify, right? Yeah. So then, suppose I take like this one is my A two, right? But 0, because I've changed the number already. Okay. So what is the, how do you compute A022? How do you compute A022 in general? Well, I mean, you have to take A22, right? Yeah. And you minus some factor, right? Say I got it K2, right? I mean, right above it. So 1, 2, right? Yeah. And so what is K2? So K2 is a factor, right? So K2 is, so here, K2 is the factor of A21 over A11, right? Because this factor allow you to get rid of these entries. Yeah. So essentially, for each entry, you need one operation. You need one multiplication here and one addition. Yeah. So sorry, one minus. So one addition and one multiplication for each entry. Yeah. So in the entry of this submatrix. Yeah. And how many entries totally? So now how many entries totally? Well, this one we have n entries, yeah? And then this submatrix, how many entries do you have? Anyone? So how many entries for this submatrix? Are you still there? Yeah, n minus 1 times n minus 1, yeah? So n minus 1 square. So in this one, I have n minus 1 square entries, yeah? So I have this n minus 1 square entries. Okay, so it means that the first stage, okay, the first stage is when I transform those entries into zeros, needs n minus 1 square entries multiplied by 2, right? Because one entries, I need one addition and one multiplication, yeah? And you see now, remember LU factorization, first you make this one equal 0, well, not LU factorization, but Gaussian elimination. But Gaussian elimination is exactly the same as LU factorization. First you make this one equal 0, then you make, you know, those equal 0 and make this one equal 0 and so on. Yeah. So then the second stage, for the second stage, you need to n minus 2 square operation. Okay. And the very last stage, yeah. So the last stage is n stage, yeah. Okay. Then you need 2 times 1 square, right? Operation, yeah. And now you just need to add up. So if you add it up, then essentially you have 2. The 2 is the big factor, right? But you have n minus 1 square plus n minus 2 square plus n minus 3 square and so on up to 1. Okay. And, you know, I mean, totally, if you sum it up, yeah, If you sum it up, those numbers, so there's a formula for this, okay, and it would be 2 times n cubed over 3 minus n squared over 2 plus n over 6. So this one, I just get a formula for sum of n, sum of square of the numbers, yeah? So from 1 to n minus 1 square, just got this. So now you ignore the lower terms, and this one is just all 2n cubed over 3. Okay, so this is the cost of the LU factorization, which is the same as the cost of the Gaussian elimination. Yeah. So when you say the first stage need to n minus 1 square. Yeah. Floating operation. Yeah. So what I want to say is need floating operation floats. Yeah. Yeah. Because you see, for each entry, I need one addition and one multiplication for each entry, right? Which means that I need 2 flops. Or even big O, right? Big O. Remember, we use a big O notation. So this one is a big O notation. Remember, we studied in chapter 2. The big O notation, well, essentially you just ignore the lower order terms when n go to infinity. So what is the largest order? Okay, that is what it means by the big O notation. So we mentioned about this in chapter 2, right? Yeah. Okay, so any more questions? So essentially, so that is how I claim that the LU factorization takes 2n cubed over 3, okay, flops. And if you ignore the constant 2/3, you can say that it's just a big O n cubed, okay? So the big O notation essentially allows you to ignore the constant, the lower terms, and the constant in front of the largest order, well, essentially when n go to infinity, yeah? And then once you have the LU factorization, then solving Ly equal B, or solving, so Ly, remember, is a lower triangular system, or solving Ux equal Y, use only about 2n square floats. Okay, so this one need to be explained. So I mean, let me explain it again explain a bit on the piece of paper, yeah? So now you have the LU factorization, right? So now you want to solve for Ly equal B, right? Or say Lx equal B, for example, something like this, yeah? So how many flops do you need this? Well, so this one, I assume that you have L11, X1 equal B1, right? And then, well, maybe we write a full L21, X1 plus L22, X2 equal B2, right? I mean, you have the full system, yeah? So 31, X1, L32, X2, L33, X3 equal B3, and so on, up to Ln1, right? X1 plus the last entry is Ln Xn equal Bn, right? Yeah. So now how do I get X1? Well, so X1 equal B1 divided by L11, right? So this one is 1 flops, because you need only 1 division, yeah? And then you have X2. Okay, so what is X2 now? So X2 is B2 minus L21 x1 divided by L22, right? So then you need one multiplication, one subtraction, yeah? So one multiplication, yeah, one subtraction, and one division, okay? So one, so how do I say that? So one multiplication, so I say one multiplication, one subtraction, yeah, and one division for the moment, yeah? And then x3, I have B3 minus L31 x1 minus L 32 x2 divided by L33, yeah? So again, so now I have two multiplication, okay? So two multiplication, two subtractions, yeah? And one division, okay? So essentially you can go on up to xn, yeah? And remember xn, then you need like n minus 1 multiplication, right? And n minus 1 subtraction, and then one division. Okay, so now you just need to sum up on the terms, yeah? So the number of, so this one is a number of multiplication, yeah? So this one is multiplication. So I cross here, but it just means that multiplication and not x. Sorry about the writing. So the number of multiplication, yeah? We equal, so this one is, the very first one is just one division. So we have to write one division here, yeah? So the number of multiplication will be, so noted in the first one, yeah? And then after that you have 1 plus 2 plus 3 up to n minus 1, right? And then the number of subtraction. So for subtraction, yeah, you made the same. So 1 plus 2 plus 3 plus n minus 1, yeah? And the number of division, you just equal n, you just sum it up, okay? And now the total number of flops. So you see this one, you can have a formula, remember? So this one is just n, so you take the sum of the first and the last term, multiply by the number of the pair. So this one gives you n minus 1 over 2. So the total flops, it just equal n plus n minus 1. Okay, so again you have 1/2 here. So it just gives you n squared. Okay, so solving the lower linear system take exactly n squared floating operation. Okay, so you count it just by hand. Yeah, and you use some formula. So, you can do the same for the upper triangular. So I will not do that. But essentially, that show you the claim that Ly equal B and Ux equal Y. So each of them use only n square flops. So two of them is 2n square flops. Okay. So now, what is the conclusion? So the conclusion is, for n very big, then the cost for the LU factorization is much, much bigger than the cost for solving the LU, I mean the lower triangular and upper triangular linear system, right? So now remember what we've done in the, so now if I go back to my script, yeah, if I go back to not this one, but the other one, yeah. Okay, so this one is the, suppose you have an n by n matrix, yeah? And if you solve it by Gaussian elimination, okay, so Gaussian elimination, the cost is about n cubed for the size of the matrix. So the total cost is just like, you know, the number of floating operation. Okay. And see, if you use the first approach, then it will be about n. N is the number of the linear system, capital N, yeah, multiplied by n squared. Okay. So total cost, yeah. And if you use LU factorization, well, initially you have to compute the LU factorization. That will take you about n cubed operation here. But once you got the L, the U matrices, then you solve, you know, only the lower triangular and upper triangular system, and each of them take n squared. So then the total cost will be O n squared plus, you know, O of 2n squared multiplied by n. So you see that for big N, for big capital N, big small n, then you see the second one will be smaller, right? Because you see, I mean, if you take n to be very big, the second term can be very big. And this one multiplied by n squared. Yeah, but this one multiplied by n cubed. So think n is 1,000, you know, it will make 1,000 times difference. Okay, so that's explained, at least in the sample, why using LU factorization is faster. Okay, so does it make sense? So any question? So does it make sense now? Yes, n is the number of the inputs, yes. So you see, because here, so this one is here, capital N is the number of input, and little n is the size of the matrix. Here, A is an n by n matrix. Okay, and we counted the flops of two methods. And you can see that, you know, I mean, for capital N is big, okay, then the first method will take more flops, so it will take longer. So remember, the number of flops is the number of floating operation the CPU have to carry out. So it will take longer if you have more operations. Okay. Does it make sense now? So I explained the lab's question yesterday as well. So if you went to the lab yesterday, so we have to solve M linear system. Okay. And there's two ways to do that. First way, and the matrix doesn't change. Okay. So here, the key point is the matrix doesn't change. So that's why you can compute the LU factorization only once. But if the matrix is changing, then, you know, I mean, there's no use. Okay. So this one assumes that the matrix A is fixed and the right-hand side is changing. Okay. So any more questions? Okay. So now we go back to the slide. Yeah. So now this one is a script you can run on your machine, and when you run it, what it does is it computes the LU factorization and it measures the time, and then it will show you that the time will around n to the end of the cube. So remember, for for the theory, we show that, you know, the order of the time taken to compute the LU factorization should be n cubed, and this one is just empirical way. You know, just ask MATLAB to compute the LU factorization with a different size matrices, and then you measure the time, and then you measure the rate of of the order. So let me explain a bit here. So you see TLUK, yeah. So here we, if you focus on this line, okay. So let me explain a little bit about this line. So because the previous slide you saw it already in the lab, yeah. So this one just make a random matrix, yeah, and then compute LU factorization. So the mysterious part is only this line. So what does it mean? So now go back to the piece of paper, yeah. So suppose I have, a matrix of size n1, okay, and the LU time, so the LU time, so PLU, right, 1, say equal 1, 2, 3, 4 seconds, yeah, okay. But assume that, okay, I will assume that this one will be some constant n1 to some power p, yeah. So p is not known, so p and c not known, okay. So this one, you run the experiment, yeah. So you run the MATLAB, you got this number, and n1 is given as well. So n1 maybe say 200, for example, yeah. So n1 is known, TLU1 is known. But now this is your assumption. So this is your assumption. You assume that it will be of order n1 to the p, yeah. And now the question is, how do you find c and p, right? So the theory say that c has to be what? So it's not known from the experiment, but it's known from theory, right? So one from the theory, what is p and what is c? We just discussed in the last slide. So you do not know. So have you got coffee in the morning yet? So anyone? Okay, so I assume that you haven't got your coffee in the morning, yeah. So anyway, so suppose now you run another experiment, yeah, for n2. Okay, say n2 is 500. Then you get the LU2. Okay, and then okay, you got some number, but now I assume that this one is CN2P. Okay, and now I have, if I take the ratio L1 over N2, then the constant got cancelled. So I got N1 over N2. Sorry, this one is not N1 over N2, but should be TLU1, yeah. So this one is still okay, yeah. So now what I want is I want to take the ratio TLU1 over TLU2, right? Then I will have the CN1P over CN2P, right? And the constant got cancelled, so I got N1 over N2 raised to the power P, yeah? So what does it mean here? So if I take a logarithm, so any logarithm, okay? So logarithm of any base to equal P logarithm of N1 over N2, okay? So at least this formula gives me what is the power P. Yeah, so you just take the ratio between TLU1, TLU2 divided by logarithm of N1 over N2. Okay, so that is exactly the ideas behind the the commands in the MATLAB. So if you go back to MATLAB, to the slide, yeah, you see, so this one P, yeah, is TLUK, okay, over TLUK minus 1. Yeah, so think this one is like 2 and this one is 1. And this one is n equation k over n equation k minus 1, right? Because the n equation is just 500 multiplied by 1 and then multiplied by 2 and so on, yeah? Okay, so if you run it, so you just spend some time and run it and you will see what it means. Okay, so spend some time running it. Is it clearer now or are you still there? Yeah. Okay, so now suppose I can run it for you. Yeah. Suppose I run it. So the time LU, the script is time LU. Time. So the script is right here. Yeah. Exactly in the lecture notes. Yeah. And you see that, okay, so n is 500, so the size of a matrix, and then 1000, 1500. So keep increasing by 500, yeah? And this is the time spent to compute the LU factorization, okay? And this is exponent p. And you see that the exponent, okay, so give you different values, but on average, it's very close to 3. Okay, so remember that we say that the LU factorization, the cost has to be around n cubed, yeah. But you know that is only for very big n. So for big n, so n is for 4,500, so close to 3, yeah. So this one dropped a bit. So, but you see, I mean, the problem is because the theory assumes that there is no other processes running in the background. But you know, in your computers, there's always some other processes try to compete with MATLAB for resources. Okay, so you don't have the ideal condition. In an ideal condition, exponent has to be around 3. Yeah. Okay, so we go back to the slide. Okay, so this one is another one. If you run on your computer, you might get a different number as well. But you see, this one give you something close to 3, you know, not exactly 3. Okay, so now you see that LU factorization is fast already, but sometimes you can do a bit faster. Yeah, and that is the case when you have a symmetric and positive definite matrices. Okay, so what is a symmetric matrix? A symmetric matrix is just when you transpose it, then you got the same matrix. Yeah, and what is a positive definite matrix? So positive definite matrix, okay, is just a matrix that when you take this expression x transpose Ix, yeah, that is positive for all vector x except x equals 0 vector. So can you give me a very simple positive definite matrix, say for n equal 2? And for n equal 1, it's not a matrix, right? But for n equal 2, the size is 2 by 2 matrix. So can you give me a simple definition, a simple example of a positive definite matrix? Are you still there? So what is the example of a positive definite matrix. Yeah, 1, 1, 1, 1. Yeah, just suppose, you know, I mean, you take take 1, 1, 1, 1. Let me share the piece of paper, right? So suppose you have but we have to check. I say this is, it might be correct, okay, but might not be. Let me check. So A is 1, 1, 1, 1. So we'll check with the definition. Okay, is it positive definite matrix or not? Well, we have to check. So if you take A, if you take X transpose AX, okay, then it means that you have X1, X2, then 1, 1, 1, 1, then X1, X2, right? So this one I just write down the definition. And then this one gives me X1 plus X2. This one gives me X1 plus X2. Okay. And this one X1, X2. Okay. Then give me X1 plus X2 plus, yeah, so X1 X1 plus 2 and then X2, X1 plus X2. Okay. And so this one gives you X1 square plus X1, X2. So plus X2, X1, so 2X1, X2, X2 square, right? So then this one is X1 plus X2, everything square. So this one is correct. So it's greater than 0 for non-zero vector X. Yeah, and it equals 0 if X is a 0 vector. So that's correct. So it's a positive definite matrix. Okay, so it's a seamless. Well, I mean, even you can take just identity. Identity can even similar, right? Identity, then you just have X1 square plus X2 square. Okay, but at least this one is a good example, right? So 1, 1, 1, 1 is a positive definite matrix. But this matrix is singular, right? Because the determinant equals 0. Yeah. So it's positive definite, but it's a singular matrix. Okay, but if you take identity, if you take 1, 1 here and 0, 0 here, then you just have X1 square plus X2 square. And it's still positive definite. Okay. So that is a definition of positive definite matrix. And yeah, so this one is another example for 3 by 3 matrix. Yeah. And this is a bit complicated, but when you expand it, then you can make it into a sum of 4 squares. Yeah. So then it will be positive for non-zero vector X. Okay, so there is a criterion to check for positive definite matrix. So if you compute the principal matrix of order K, and you take the determinant and order them positive. Okay, so this is example here. So you take the first one, then just 2, and then take the principal matrix order 2, then you got this 2 by 2 matrix, and you compute the determinant, and all of them are positive. It's positive definite. And then another criterion is, you know, if all the eigenvalues are positive, then the matrix is positive definite. Yeah. So I think we don't have time to go further, but I think we can continue next week. Okay. So we will stop here.